Hello, welcome to Noise Control and its Management. Today is the second last day of this week, and what we will discuss today is all about indoor barriers. How do we go around designing them? So, unlike outdoor applications, for indoor barriers, a significant difference is that we also have a significant amount of reflected or reverberant sound. Okay. So, if you have a large room, and this is a barrier, some sound may directly reach the person through reflections, and then some sound will get obstructed as it reaches the listening position. Okay. So, indoor barriers are particularly effective if most of the sound reaching listener is direct in nature. Okay. Other way we can say is the same thing, that indoor barriers are effective when direct sound field is much stronger than the reverberant sound field. This is. Now consider the situation that we have a large room and there is no barrier. So, this is our sound source, this is the listening position, this is emitting W watts. So, here the sound power level is LW, the sound pressure level is LP, and if there is no sound, no barrier, then how do we predict? Suppose this distance is R, then LP is equal to LW plus 10 log of 10 4 by room constant plus Q by 4 pi R square plus 0.1, right. This is the relation we have discussed till so far. Once the barrier is introduced, think about it, what happens? Suppose I introduce a barrier here, what I have effectively done is that I have introduced I have done two things. I have introduced two more reflecting surfaces. This is the first reflecting surface, right. So, sound will come here and it will get reflected and it may bounce and it may still reach here. That is one thing I have done. So, once I have added a reflecting surface, this R will change, which is room constant, right. The value of R is going to change. So, I can use the same relation maybe if I can adjust for the room constant. The second thing which I have done is that the diffracted sound, diffracted sound goes like this, which is distance A, and it comes like this. So, original distance was R, but now instead of R I have to replace this by A plus B, because the sound which goes directly to the listening position travels a distance of A plus B. So, this R becomes A plus B. The third thing is that not all the sound goes to the other end, but only a portion of it goes to the other end, right. And how much of it goes, the amount of sound which reaches the other end is, some of the sound is transmitted and that fraction is AT, and some of it is diffracted and that is AB. So, instead of this thing in the numerator, I also introduce a new term, right, and that is AT plus AB. So, if I have a barrier, then the value of LP can be calculated by LW plus 10 log 10 of 4 over room constant, but the room constant with the room with the barrier. So, I will call it RB plus directivity of the source times AB plus AT. If all the sound was getting transmitted or diffracted, then this number will become 1, right, but only a fraction of it is going to the other end, divided by 4 pi times A plus B whole square plus 0.1. So, the other question is that, okay, we know how to calculate AB through the relations which we had discussed earlier, we know how to calculate AT, we know what is A and B, how do we calculate the revised room constant? So, the answer to that is simple. So, RB is equal to, so the original relation was what? R was equal to alpha bar S naught divided by 1 minus alpha bar, this was the original relation. But now we have some extra reflecting surfaces, so I have to account for that. So, it is now alpha bar S naught plus I have some more surface. So, let us say the surface of barrier is SB times alpha 1 plus alpha 2, and what are alpha 1 plus alpha 2? Let us say alpha 1 is the absorption on this surface and alpha 2 is absorption coefficient on the second surface, because there are two surfaces which are going to absorb sound. So, it is, so this is the total area times their absorption coefficients, and in the numerator also I introduce these things. So, first I compute RB, and after I compute RB, then I can use that RB to compute LP. So, this is there. I have to make couple of other observations. This term is because of reverberations. Because of repeated reflections. This term is because of direct sound field. Okay. I mean, when I say this term, this, it means this entire thing, and same thing here also. So, the barrier will be in particularly more efficient if this direct sound field term is much larger compared to the reverberation term, and we will actually do an example and we will see that, because there is only so much you can change RB, but this you can significantly influence. So, if the direct sound field is strong in the room to begin with, a barrier can do a very good job in terms of reducing the overall sound pressure level. So, we will do an example. So, here there is a machine and it is generating 109 decibels. This is the sound power level at 1000 hertz. So, for 1000 hertz band it is generating 109 decibels, and This machine is in a room. The dimensions of the room are 30 by 30 by 5 meters. Okay. So, we will actually draw it. So, this is 30 and this is 30 meters wide. So, it keeps on continuing on the back and the height is 5 meters. And let us say the machine is somewhere here. And then there is a person who is operating it, and the person is remotely controlling the machine, or he sits there and whenever he has to change, he comes and changes the machine, but he is hearing a lot of noise coming from this machine. So, this is the machine source and this is the listener. Okay. And both of these guys are at a height of 1.5 meters away from the floor. Okay. So, the person is standing and maybe he is also sitting on some raised platform. So, his ears are 1.5 meters above the ground. Okay. And the overall distance between these two individuals is 3 meters. The directivity of the machine is 2, directivity factor is 2. So, the question is, if I introduce a barrier, what will be the sound pressure level, and if I do not have the barrier, what will be the sound pressure level that is at this location. Okay. So, to know that, I have to give some details of the barrier also. So, on this surface alpha 1 is 0.2 and on the other surface alpha 1 is 0.9, and the barrier is overall 3 meters tall. The height of the barrier is 3 meters. Okay. And the speed of sound is 347 meters per second. Finally, the dimensions of the barrier. So, this barrier is 3 meters tall and the size is 5 meters by 3 meters. So, it is 5 meters in the depth direction normal to the plane of your television screen or laptop, and it is 3 meters tall. So, these are all the data on the problem, and the question once again is, what is the value of LP without barrier, what is this value, and LP in presence of barrier with barrier. We have to compute these. So, what we will start with without the barrier condition. Okay. So, without barrier, I know that for a closed room LP equals LW plus 10 log of 10 divided by 4 over R plus directivity index divided by 4 pi R square plus 0.1, but I do not know the room constant. So, I have to calculate the room constant. Okay. So, to calculate the room constant, I have to know the internal surface area. So, surface area of the room is how much? 30 times 30 plus 30 times 5 plus 30 times 5 times 2 is equal to 2400 meters square. And then I forgot to add one data which is also given is that the average surface absorption coefficient of the room is 0.35. Okay. So, with that understanding, the room constant is what? Alpha bar times S naught divided by 1 minus alpha bar, and that works out to be 1292 square meters. So, now I know R, so I know this value. Q is specified as 2, it is given, Q is equal to 2. So, LP, sound pressure level at the location of the listener, is LW is 109 decibels plus 10 log of 10, 4 by 1292 plus Q, 2 divided by 4 pi into 9 plus 0.1, and that is equal to 92.3 decibels. So, again this is a very high sound pressure level, we do not like this at all. The person will go deaf if he gets exposed to this pressure level for extended periods of time. So, we want to reduce it. So, our next job is with barrier. So, before we compute this, I also wanted to show you some numbers. So, if you do this 4 over R, you calculate, you find that its value is 0.003095. Okay. 4 divided by basically 1292, it comes to 0.00395. And Q divided by 4 pi R square, this if you do the calculation, it works out to be 0.01767. Now, we had said earlier that this term is related to reverberations and this term is related to direct sound, and we see that the magnitude of the reverberation component is very small compared to the direct sound field. So, because we are seeing this, we think that if we put a barrier in this situation, it will work. If these numbers were close to each other, or if the direct sound field was weaker than the reverberant field, then we would not consider barrier as a potential solution. So, now we go back and we compute RB. So, what is RB? RB is 0.35 times 2400 plus the area of the barrier, and area of the barrier is 5 times 3 into alpha 1 plus alpha 2. So, that is 1.1 divided by 1 minus alpha bar minus area of the barrier 15 divided by area of the room 2400 times alpha 1 plus alpha 2 1.1. So, that works out to 1332 square meters. The next thing we compute is A. So, what is A? A is this distance and this is B. So, A is basically this distance is 1 meters or 2 meters. This is 1, it is given, and this is 2. So, this is 1 square plus 1.5 square, the whole thing is square root, Okay. So, A is equal to 1 square plus 1.5 square is equal to 1.803, B equals 2 square plus 1.5 square equals 2.5. So, now we have computed A and B, and where do we use this A and B? We use AB in this relation, but we also have to compute barrier coefficient, and the barrier coefficient we compute by first finding out Fresnel's number, which we discussed in the context of barriers outside, and then you use that tan hyperbolic relation to compute the barrier coefficient. So, Fresnel's number n equals 2f times A plus B minus D divided by C, and that is equal to twice of 1000 hertz times 1.803 plus 2.5 minus 3 divided by C. C is 347, and that is equal to 7.51. So, again it is less than 12.7. So, AB equals tan hyperbolic square of root of 2 pi n divided by 2 pi square n, and if you do all the math you get 0.006747, and then AT, which is the transmission coefficient for the barrier, is what? 10 to the power of minus transmission loss by 10, and the problem tells us, okay, maybe I did not specify earlier, which is my mistake, transmission loss for this barrier we are specifying it as 31 decibels at 1000 hertz. So, this is one data I had omitted, I am sorry, but this transmission loss number will help us compute AT. So, this is equal to 10 to the power of minus 31 divided by 10. So, that is equal to 0.000794. So, now with all this data we compute LP. LP equals LW plus 10 log of 10 4 over RB plus times AT plus AB divided by 4 pi times A plus B whole square plus 0.1. So, this equals LW is how much? 109 watt decibels plus 10 log of 10 4 divided by 1332 square meters, that is the room constant with the barrier, plus directivity index is, or directivity factor is 2 times AT 0.006747 plus 0.000794 divided by 4 pi times 1.8 plus 2.5 square plus 0.1. Okay. So, we will, I can directly write the answer, but I wanted to show you something extra. So, I will actually compute these numbers. So, 4 by 32 it works out to be 0.03004. Okay. And this other term it works out as 0.0000, 4 zeros, 648 plus 0.1. Now you see this term q over 4 pi r square was attributable to the direct sound field, it was 0.01767. This number has gone down very significantly, almost 99% of that thing has vanished, because this is the direct sound field term. This number is the reverberant field term, it was 0.03004 and it was 0.003095. So, not a whole lot of difference between these two. Okay. So, once again we are seeing that the barriers do a good job in reducing the direct sound field, but not such a great job in reducing the reverberant sound field. So, finally I do is 84 decibels. So, LP without barrier was how much? 92.3 decibels, and LP with barrier is how much? It is 84 decibels. And most of this reduction has come because of reduction in this term. Now, if I reduce this term even further, this 84 decibel will not go down any significantly, because it is already pretty close to 0, right, it is already pretty close to 0, but the barrier will do a bad job, will not do such a great job in reducing this term. So, if I want to significantly go down below 84 decibel level, then I have to do something different than just a barrier. The barrier, this is probably my limit up to which we can go down to in closed doors. In open doors situations, this term will not be there, so does not matter, but in closed doors this term does not change much, and this is probably the roughly the lowest possible value which I will get in terms of LP. So, we do get good amount of sound reduction in case of barriers located inside a room, but the magnitude of this sound reduction from barriers which are located inside the room is not that large as compared to the, if you place the same barrier outside, it is a much larger reduction. So, that is all I wanted to discuss for today, and with this I conclude our discussion. We will meet once again tomorrow, which is the last day of this class, and till so far we have been thinking of how to control and reduce noise levels by either stopping them or reducing the overall sound power level. Starting tomorrow, we will start looking at different ways, some other ways, specifically how we can suck in, not necessarily absorb the sound, but suck in a particular frequency by using some specific resonators and things like that. And specifically we will use this term called Helmholtz resonator. So, if you have a particular sound in a room or outside and it's dominated by one single frequency, then probably you can use something known as a Helmholtz resonator to reduce that sound by a significant fraction, because that resonator has an ability to absorb or suck in a particular frequency very effectively. So, that concludes our discussion, and I look forward to seeing you tomorrow. Bye.